Hey guys, so in this video we are going to be talking about rotational motion. And so the first thing with rotations I want to talk about is just plain circular motion, which is probably obviously the most, the simplest case of rotational motion. And so in this setup I've got a mass m going, it's got a tangential velocity v, right? It's just moving this way, but then it is going to be moving in a circle. So pretty soon, this mass, when this mass is here, its velocity will be going like that then, right? So its velocity will keep on changing, right? Not change, so it's going to be going the same speed. Well, not necessarily the same speed, but we'll talk about that in a minute. But just in the absolute most simple case, it is uniform circular motion, which means it's going with the same speed, but its velocity will change. So its velocity is always going to be tangential here, and it will just go around the circle. So the first thing we know for circular motion, and this is probably, you're probably familiar with this, there is an acceleration because the velocity is changing. Now, I will link a video to this about why the acceleration is actually directed towards the center, but it does turn out that if it's going in uniform circular motion, it has an acceleration. We'll call this the centripetal acceleration. And this is going to be provided, of course, by a force, right? Things don't naturally move in circles. You have to have a force. So sometimes that will be like the force of gravity for like a satellite orbit, or in for the basic elementary model of an atom, right, where you have an electron orbiting a proton, the force causing the centripetal acceleration is going to be the electromagnetic force. Or a lot of the times when you can do this at your home, you just swing a rope around with something at the end, right? The centripetal force is the force of tension, right? The tension from the rope. But in any case, whenever it's moving in a perfect circle, the centripetal acceleration is equal to the velocity squared, right? This is the magnitude of the velocity squared, so the speed squared, divided by the radius of the circle, right? Um, okay, so now we can define a few rotational quantities as well. So we know it has a velocity v, right? If it in a circle, it also then has an angular velocity omega. And omega is equal to v divided by r, right? And what omega is in a minute, right? Or not in a minute, but just in a small period of time, right? You're going to see, and I'm gonna just erase what we have with the centripetal acceleration to make this more clear. So hopefully you've got that down. You'll know that the centripetal acceleration is indeed there. Cool. So it is not, this thing is not just going to move a distance, right? It's going to move around the arc of the circle, right? Right, so it starts here, and then it's going to move to like here, right? Sorry, that should be a straight line, right? And it's going to move through an angle theta, right? Move through an angle theta. And we want to know how many omega is measured, right? Omega is radians per second. It is the rate of change, right? It is the rate of change of the angle. This is going to be measured in radians per second. Right? Which we know radians are dimensionless, so the dimensions of this is just 1 over seconds, right? Which is sometimes why it's called the angular frequency. Well, it's a little bit different than the angular frequency, but some people will call it instead of angular velocity, angular frequency, which has the same units of radians per second, and we'll see that in a little bit. and by then, when we get into quantum mechanics, we'll see angular frequency appear with the same symbol, and it's going to be measured in radians per second, but it's a little bit different. Um, and so, uh, and so we have it moving at this velocity, angular velocity omega. Well, let's see what this is, right? We know that just in the simple case where it's moving with a constant speed, right? If it's moving with a constant speed, it's moving with a constant angular speed, right? And we can know that, so omega is delta theta divided by delta t, right? And delta theta, right? Well, if we think about S is arc length, right? S is equal to r times theta, right? Which means theta is equal to S over r, right? So this is delta S over r, right? And delta theta, r is not changing, right? Because it's just moving in a regular circle. So it's delta S over r over delta t, right? Which is 1 over r times delta S over delta t, right? And delta S over delta t, well, what is that? Well, delta S is the amount of an arc, right? Is the arc length it's moving. It is actually the distance it's moving to, with respect to time. Well, this is velocity, right? So this is equal to v over r. And notice we can do the same thing with differentials with calculus, but I'm just making it a little bit easier with this because it's moving, right? We're at a constant velocity, right? Which means ds by dt is the same as delta s over delta t, right? So that's your proof for this. Hopefully that makes sense. Hopefully this is right, review, right? I'm going to erase this. So note that omega is measured in omega is measured in radians per second, right? And so now we know, well, what if there is some acceleration? What if, right, not just acceleration towards the center, but if this is speeding up as it goes around? We know that would mean omega is increasing. And we can define the quantity d omega by dt is being equal to this quantity alpha, which is the angular acceleration, which it turns out this is actually equal to a over r, and we can just show that easily if we take the derivative of this with respect to time. Well, derivative of v with respect to time is a divided by, well, 1 over r, that's going to be a constant, right? Because r is not changing with respect to time. Right? So d omega by dt, which is alpha, the angular acceleration, is a over r, and this is measured in radians per second squared. Okay, so now I've just got 3 more quantities I want to talk about, and these may be a little bit less intuitive, and I'm not going to explain them super in depth. You can look on Khan Academy if you want to see these explained more in depth, but just basically, and I'm just going to give you a little bit of a way to think about it. If you take a rope with some object at the end and you swing it around, right? The or actually, if you take a disc and you spin it around on on something with low friction, the question is it easier to stop it if you try to stop it from moving? Is it easier to stop it closer in or farther out? And if you go and try that, right, you'll actually find that it's a lot easier to stop farther out, right? Meaning that it actually has more inertia the farther out you go, right? And for a point particle, right, that's has a mass m and a distance r away, the rotational inertia I is equal to m r squared, right? there's a different equation for like a disk, right? But for a point mass, and that's all we're going to be really dealing with in this course. So I is equal to mr squared. So I is the rotational analog for mass, just like omega is the rotational analog for V. Alpha is the rotational analog for A, right? Which makes it interesting, right? If we have momentum now, right? Which we have, right? Omega. Well, omega is V over R, right? Omega is the rotational analog for velocity. So just like we have P equals mv, we can have L, which is angular momentum, equals I omega, right? So we're going to have L, which is equal to I omega, which is equal to R mv, right? Which is then equal to R times P, right? So, and then we can have one other thing, which is torque, which is the rotational analog of force, right? And just like momentum is R times, angular momentum is R times P, right? And again, this is all just for a point mass. It gets a little bit, uh, this equation gets a little bit different for different distributions. So tau, which is torque, which is the Greek letter tau, is I alpha, right? Or this is the net torque, right? The net torque is I alpha, which is R times the net force, right? Now, this is only for circular motion, right? In fact, these equations are a little bit different for not circular motion. So that's what I would like to go on to next. So hopefully you have an intuition for how this is going to work with circular motion, right? And so let's go on to here. So here I have an axis of rotation, right? And I've got a mass m moving at a velocity v, which is not, this is not moving in a circle, right? A circle, it would be perpendicular. Notice now, instead of just the length r, I have an r vector, which points from the axis of rotation to the mass. Now, I'm not going to go super into this. I'm going to give really just a brief overview. So, the first thing, right, is omega, right? Actually, sorry. I'm going to start with moment of inertia, because that's the one thing that actually doesn't change. It still is true that I is equal to mr squared, right? Now, omega, on the other hand, right, is going to be the tangential velocity, vt over r. Now, if there is an angle, if there's some angle, right, between the r vector and v, right, which technically you're actually supposed to measure the angle tail to tail, but in terms of how I'm doing this right now, it actually will suffice. And note, this is not technically correct, but it is a way easier way to think about it, and so it's going to give us correct results, right? We measure this angle, right? And so V tangential, if you just do a little bit of trigonometry, right, which we want, V tangential is the component tangential, right? This is V tangential. That is going to be, right, if we just look, well, this is 90 minus theta, right? So theta would be here as well, right, if we had a little right triangle. So it would be the opposite, right? So this is equal to V sine theta, right? And these are all magnitudes, right? V sine theta over r, right? So this is, right, sine theta I know can be negative too, but we're just going to call it, right, this is the absolute value. This is the magnitude of angular velocity. It turns out angular velocity is a vector, and I'll show you how to actually determine the direction of these vectors. But for right now, I wanted to talk about just the magnitudes, and then we'll move on to direction, and that's going to be the last thing we do in this video. Similarly, acceleration is still d omega by dt, right, which is going to be the tangential acceleration over r, right? Hopefully you see how this is kind of generalizing. Again, I know I'm going fast. These are just things that you hopefully should know or be able to pick up or just look up on Khan Academy. Right? So now we have the more complicated parts, which is angular momentum and torque. And so the real definition of angular momentum and torque, and I'll give it in its vector form now, is angular momentum is equal to r cross p, which is a new type, right? We talked in our vector video about dot products. This is a cross product, and we're not going to be dealing with cross products for a while. We're not really going to be dealing with them until section 6, so I just want to give a brief overview right here. So, and similarly, torque is equal to r cross on f, right? Which is actually the if we're talking about the magnitude, this is equal to r, the magnitude of r, times the magnitude of p times, or the magnitude of p that is tangential, right? That is perpendicular to the r vector, right? Which is like the dot product, right? The dot product is the parallel component. The cross product is the perpendicular component, which is, this is r p sine theta, right? But notice, right, that for circular for circular motion, theta, right, is pi over 2 radians. The sine is just 1, right? So that brings that whole thing. Same thing here, right? This is r times f tangential, right, which is, or the perpendicular component, which is r f sine theta. And actually, again, I'm going to have absolute values around this, so I know it's a lot of absolute values. We're just saying everything's got to be positive here, right? And you can verify easily that this is actually equal to I omega, right? You'll see that here, right? If you take mv equals p, right? Multiply I by omega, you'll get this expression. And the same thing if you multiply I by alpha, you'll get this expression, right? So that's all verifiable. So these are all the magnitudes. Hopefully this makes sense, right? And if it doesn't, you may just want to just take this for right now, take the math with it, or rewatch this slowly, kind of see how I worked out the math. Just note the cross product, the magnitude is, right, r times the perpendicular component. Now, to get the direction, that's a little bit more complicated. And I'm going to link a video in the description that's going to talk about what is called the right-hand rule. And the right-hand rule, which, you know, I don't have my hand on screen, which makes it a lot harder to explain the right-hand rule, which is why I'll leave it to a video on YouTube. But it's a way to determine the direction. Now, I'm going to give you a shorthand for 2 dimensions, right? Which is, if in this case, right, if it's moving sort of in a circle, right, it's moving, right, you see that this mass would be moving clockwise, or sorry, my bad, counterclockwise. And counterclockwise, right, if you're looking at the plane, right, at the plane of rotation, and it's moving counterclockwise, that means that the angular velocity vector, and thus the angular momentum vector, will be pointed out towards you, right? So, but the thing with the cross product, right, is r cross p, the direction of r cross p, is going to be perpendicular to both vectors, right? So you see r is in the plane, so is the velocity vector, so the momentum vector is, right? The angular momentum vector will be pointed out of the screen. It's going to be perpendicular to both r and p, right? If it's moving clockwise, though, it's going to be pointed into the screen, right? So counterclockwise is out towards you, clockwise is away from you. And that's sort of the shorthand. If I have an acceleration, say I'm applying an acceleration this way, right? That would mean it would actually be decelerating, right? The velocity would slow down. The acceleration, right? Even though if it's not, perfectly tangential, the acceleration would make this accelerate in the clockwise way, which means the angular acceleration vector. And notice I should have these here. Hopefully you caught that. Right. And again, the tangential acceleration, I was assuming you would realize that this is just the acceleration times sine theta, right? So if I apply a force here, which would cause an acceleration in that direction, if that's the net force, or if that's the net tangential force, because remember, the centripetal force is already counted. The centripetal force is already accounted for, right? It's accelerating. It's got the force in the clockwise direction, which means the angular acceleration vector and the torque vector would be pointed away from you, right, into the screen. All right. And actually, the one last thing I wanted to do, we talked about how kinetic energy, right? Kinetic energy is p squared divided by 2m, right? Because this is, right, 1/2 mv squared, right? Well, for a point particle, also notice, and you can do this using this equation replacing p with mv, right? This is equal to L squared over 2I, which is, right, the rotational analog for this, right? Momentum becomes angular momentum, mass becomes moment of inertia, and it turns out that this also works, so that's going to be important. Okay, so hopefully this makes sense. I'm going to have look on Khan Academy if it doesn't, and I'll have links in the description about the centripetal force, and I'll also have something about the right hand rule. Okay, I'll see you in the next video.